Hi, this is Professor Fernandez, and in this video we're going to work out an example on the alternating series test. This example comes from the notes from Lecture 8. You can find those notes on this site and find these other things there as well. So let's take a look at what the example says. So first it says verify that the series below are in fact alternating series. We'll talk about how we do that in a minute. And then use the alternating series test to determine if they converge. So we actually don't know this time around if these series converge or diverge. And we actually also don't know if they're alternating series. You know, I wrote this example to illustrate the alternating series test. So spoiler alert, they probably will be both alternating and convergent. So what is the alternating series test? I'm going to zoom in here. This is the theorem from lesson 8, which is the actual alternating series test. A couple of quick takeaways from what this theorem says. First of all, the alternating series as an alternating series has a very specific form. It could come in either one of these two forms, really. Those are the only two options. Both of these forms tell you that, for example, if we write out this term, the terms in this series, when n equals 1, we have a negative and then a sub 1. If n equals 2, we have a positive, so plus a sub 2. And then it keeps going this way, right? So in other words, this version of the alternating series starts off with a negative term, right? We're assuming that all the ANs here are positive. And then it switches to a positive term, then negative, then positive. So it alternates the sign. So that's really what alternating refers to here, the alternation of the sign, SIGN, of the series. If I look at this representation of the series, what's different between that one and this one? Well, the n plus 1 here. So n plus 1 is different from n in the sense that what it does to the series is that if n equals 1, well, I add 1, so I get 2. So that's negative 1 squared. That's positive. So this version of the alternating series starts with a positive term, and then it turns negative, and then it goes positive, and so on. Because this still alternates in sign, SIGN, it is still an alternating series. So that's basically the two types of alternating series you might see. A series that starts off with its first term negative and then alternates sign, or a series that starts off with its first term positive and then alternates in sign. So the alternating series test then says, okay, assuming you have one of those two series, right? This is why we want to check first before using the conditions for the test. It says, assuming you have one of those two series, the conditions for convergence, according to this test, are that the limit of the AN is 0, and this other condition. What does this condition mean? Well, let's take a look at what it says. This is the nth term in the series. This is the next term in the series, and it's less than or equal to the nth term. In other words, as you go down the series, you want to make sure that each successive term is at most the term before it, right? So you might call this something like non-increasing. So you want the series to terms to either be doing this, that would be when they're equal, or you want the series terms to be doing maybe this, decreasing, right? That would be when it's less than. But you don't want the series' terms to be doing that. That would be increasing. That would be this term is bigger than that one. That would be this, which is the opposite of what the inequality here is. Okay, so that gives you a visual of what alternating series look like. They alternate in sign. And if you want to use the alternating series test, you want the AN to go to 0, and you want terms to be getting successively either smaller or at least not getting bigger, right? So now let's use the alternating series test for this example. Okay, so the test here is giving us sort of a four-step procedure, right? Number one, we want to figure out, I'll put this in blue here. Number one, we want to figure out if this is in fact an alternating series. So we could, for example, try to put it in the mold of minus 1 AN or minus 1 to the n plus 1 AN. The two types of series alternating series we just talked about. So we can try that, and you can see that for this example, it works very nicely. For this example, it's going to be a little more challenging, but we'll get there in a minute. For this one, it works very nicely because we already have this minus 1 to the n. So if we rewrite the series as negative 1 to the n times 1 over n, then we can see more clearly that this is a sub n. And then for sure, because a sub n is 1 over n, these are all positive terms, right? Remember, that was one of the conditions In order for it to be an alternating series, it has to alternate sign SIGN. So you want the terms, remember the minus A1 plus A2 minus A3, you want these to be positive. If some of these can be negative, then it may not be an alternating series. Okay, so we have now found our AN. We see that it's positive, and this is in fact an alternating series. Great, so number 2, now we want to start actually running through some of the checks of the alternating series test. So the first one here is we ask ourselves, is it true that this limit equals 0, right? This is the AN from our series. And at this point, you know, we've done several limit calculations in the course, and we've used a lot of Calculus 1 knowledge from that for calculating limits as n goes to infinity. So we did this in the context of sequences. We also did this in the context of series. So I'll send you over to a few other videos in this playlist if you're interested in seeing how we did that for sequences. That's that video. Some of the videos in lesson 6 also do this in the context of the divergence test for series. So I'm going to, I guess, repeat some of what I said there, but not too much, so that we can get to the alternating series part. So this limit is pretty straightforward. It is in fact 0 because the denominator gets bigger and bigger and bigger, and we're dividing by just a giant number, which gets closer to 0. So I'm going to write a little arrow here to say, indeed, this is verified. And then in terms of the alternating series test, right, what is the next thing to do? Well, so we figured out that this limit is 0. So now the last check, if you go back a few minutes to the video where I talked about the theorem itself, is it true that AN plus 1 is less than or equal to AN for all n? So remember, this meant that the sequence is well, it is a sequence, but the terms in the series are not increasing, right? They are either staying the same, constant, or decreasing. So how do we get this to work out? Well, I'm going to actually show you that there are quite a number of different ways you could establish this. And it's going to seem silly what I'm about to write out, but this is good information for you to know because it gives you options. And some of the ways of showing this condition that I'm going to discuss in a minute are going to be easier than others for certain problems. So bear with me for a second. So the first way that you might want to show this is by just doing it directly. So what would it look like in this problem? Well, the AN is 1 over n. So AN plus 1, everywhere we see an n, we put in an n plus 1. And then AN is just 1 over n. So then you want to ask yourself, is this true? For some problems like this one we're looking at, it's fairly simple to figure out if this is true or not. For other problems, you might have to do some algebra. But we're back to inequalities, right? Which we were talking about that with the direct comparison test in the previous video, the videos for lesson 7. But here you can see that because n is bigger than or equal to 1, right? I'll just scroll up, remind you that's where the series starts. You know, it's good to keep that in mind. Actually, doesn't really matter here, but if we look at this inequality, then what we're saying is we're taking n plus 1 in the denominator here, and here's an n, and n plus 1 is always bigger than n. So when you take the reciprocal, it's always going to be smaller. For example, like 1/3 is bigger than 1/2. Sorry, it's less than 1/2, right? So this is one way to talk it out. But if you wanted to show this on an exam or something, you might start with doing a reverse proof, which I talked about in the video for lesson 7. So for example, you might start with, well, if I assume that this is true, which is, you know, again, bad because that's what we want to show. If I assume that this is true and I cross multiply, I would get n less than or equal to n plus 1. And, you know, again, it's inequality, so you want to be careful when you multiply or divide by something that there are no negative numbers around that would flip the inequality sign. But this is the importance of knowing that n is bigger than or equal to 1. It doesn't do any of that flipping. Okay, so back over here, this is true, right? If I have a number and then I add 1 to that number, then the new number is actually strictly greater than, not just, you know, greater than or equal to. It can never be equal to. So if I start now from this fact to do the formal proof, I would say, okay, n plus 1 is bigger than n, right? And there's really no reason to argue anything more than that in a Calculus 2 course. And then if you take the reciprocals, that flips the inequality sign, right? and I get to exactly what it is I want to show. So again, this is a very formal way to show that this inequality is indeed true, and in fact is stronger than less than or equal to, which is less than. So that would be it for showing an plus 1 less than or equal to an for this example in this way. And then we would therefore conclude converges, right? Because if I scroll over again, we've verified that the limit goes to 0 and that the series' terms are non-increasing, right? They're either staying constant or decreasing or doing, oscillating between one or the other. Okay, so let me show you now the other two ways to do this that might come in handy, and we'll use a different one of these two other methods in the next example in a minute. So what is the second part? Well, this one just straight up writes out the inequalities and just works with that. The second version divides both sides by a sub n. Again, we are assuming that a sub n is positive, which is part of what it means to be an alternating series, so we can divide by a sub n. Okay, so this one asks, is it true that the ratio of successive terms, an plus 1 to an, is less than or equal to 1? Let's write out what that would look like in this example. So again, an is 1 over n, so an plus 1 is 1 over n plus 1. So that's here, 1 over n plus 1. And then I am dividing by an, which is 1 over n. So that's the same thing as multiplying by the reciprocal. So that's n over n plus 1. And then question, is this less than or equal to 1? Right? And then now this is a different way of showing the same condition for the alternating series test. And it leads to potentially different manipulations that you could do. That might be easier than what you did before when you did the original way. So for this one, again, we can reason this out in a variety of ways. Number one, we can say the denominator is always 1 bigger than the numerator. So actually, for sure, we can say that this is strictly less than 1, and then just stop there. We could also say, okay, what if I add 1 in the denominator and also subtract 1? Okay. In other words, I conjure up a 0 in a very clever way. Right? If I group these together, then I can divide these out. That gives me 1. And then minus divide these out, 1 over n plus 1. And I notice now that, again, because n is bigger than or equal to 1, for example, when n equals 1, this quantity is 1 minus 1 half, which is 1 half, definitely less than 1. When n equals 2, the next one is 1 minus 1 over 3, which is 2/3, also less than 1. Right? So you can see that because I start with 1 and I subtract always a positive number, this quantity, again, is definitely going to be less than 1. So again, it checks our requirement that a sub n plus 1 over a sub n is less than or equal to 1. So that is the second way that you could show that little that second part of the alternating series test. And then let me show you the third way, again, to give you options for when you're going to use this in practice. The third way is to go here and then just subtract the a sub n. So a sub n plus 1 minus a sub n less than or equal to 0. Okay, that's the third way. So again, options for showing all of these different things. So if I just clean things up here, we can see really what these options are. And then let's talk about this last option. So in this context of this example, a sub n plus 1 was 1 over n plus 1. A sub n was minus 1 over n. And I'm asking myself, is this less than or equal to 0? How do I work this out? Well, one way is to find a common denominator. I'm just going to multiply the two denominators. And then this fraction here, right, you can do the cross multiplication or you can do what I'm about to do. I would multiply this one by n, so that's the numerator here, and I would multiply this one by n plus 1. Okay, so minus n plus 1, that's the numerator here. The minus coming from here and the n plus 1 coming from there. Okay, and then now I just simplify this. So what does the numerator look like? If I distribute out this minus 1, I get n minus 1. So that's n's cancel. I get negative 1 over n plus 1. Okay, and now I have simplified it. I have done the algebra. Now let me step back and answer my original question. Is this difference less than or equal to 0? The answer here is pretty clearly yes, right? We have a negative number here, and then everything in the denominator, because again, n is bigger than or equal to 1, everything in the denominator is positive. So this is actually less than 0 for all n, strictly less than 0. So yes. Okay, so the big takeaway, no matter which way we try, we can show that in fact this is true. And again, these are three very different ways to show that. In this example, if we now step back and look at which one might have been easier to do, it really just depends, right? So this one, remember, left us showing this. This one left us showing that, and then this other one left us here. So if we look at these three, I would probably argue that this is the easiest one to see. It's pretty clear that these terms are negative. Next, I would probably argue that maybe this one is easier. You have to do some reasoning, right? This one effectively converts to reasoning that n plus 1 is bigger than n, and then kind of taking the reciprocal and undoing that, getting here. And then this one, I think, is not far behind. But if I were to rank these three, right, I think might have an easier time convincing your professor or someone that this is in fact a negative term for all n. Okay, so that does it for this example, right? This thing definitely converges, this series over here, right? So now let's go back and look at the second example. We'll speed things up a little bit, and now we have three different approaches to verify the last requirement in the alternating series test. Okay, so remember the first part, like we did here, is to actually, verify that this is an alternating series. Pick out the AN also for later to find the limit and check that condition. This one doesn't look so easy to see that it's an alternating series. But remember, all that matters is that the series' terms actually alternate. So one way you could establish this is you could, for example, make a table. We could do some algebraic manipulations here to try to get, this entire term to look in the alternating series form like this or like this. But really, the time it'll take you to do that is not worth it. I would just, convince yourself that it's an alternating series. How do you do that? Write out the first few terms, and you'll see its alternation or not, right? So if n equals 1, for example, I'm putting it into here. I get minus 2 to the 0, so that's 1. If n equals 2, I'm going to write out minus 1 to the 1, right? Because n equals 2, 2 minus 1 is 1, times 2 to the 2 minus 1. Okay, and then for 3, if n equals 3 here, I'm going to get a negative 1 to the 3 minus 2, negative 1 squared, times 2 to the 3 minus 1. And then for 4, negative 1 to the 4 minus 1, that's 3, times 2 to the 4 minus 1, 4 minus 1. So you can see here the alternating nature of the denominator. And I'll tell you in a minute why I focused in on just the denominator. I just want to write these out so you can see it very clearly. And then we can predict, the term with n equals 5 here. We're just incrementing all the powers here. Okay, so why did I pick on the denominator? Well, the numerator is n, right? So that's always positive. That's not going to alternate in sign. The denominator is the only one that could potentially alternate in sign. And what we see now here is that we have a negative, or actually first we have a positive, then we have a negative, then we have a positive, then we have a negative. That's an alternating denominator in sign. And, just like if I take, 1 and I divide it by negative 2, that's negative 1/2. Or I take 1 divided by, negative 4, that's negative 1/4. These negative signs in the denominator pop out to be in the numerator or in front of the fraction, however you want to think about it. So again, we get back the behavior that we talked about earlier, where if I write out the terms of this series, right, the first one is positive, and then I get a negative, and then positive, negative, and so on. So this is in fact an alternating series. And I'll just pause really quickly to point out why this is so important by contrasting it with another series. So for example, what if I look at the series n goes 1 to infinity of cosine n? Okay, this one is easier to write out, right? Just cosine 1, cosine 2, cosine 3, so on and so forth. Question, is it alternating? The answer is no, right? So cosine of 1 is positive. Remember that cosine of pi over 2 is 0. Pi over 2 is, 3.14 divided by 2, so it's, I don't know, about 1.5-ish. So It's so 1 is less than 1.5, so it's positive, right? So this is positive. Cosine 2, cosine 3, as you go further down in series, what you'll discover is that it isn't a perfectly alternating series, right? Some terms will start off positive, and then you might have a negative term, and you might have another negative, and then a positive, and then a positive. That's because ultimately, right, cosine oscillates, and what we're doing in the series is we're kind of sampling it at a bunch of random points, some of which are going to be above the y-axis, some of which are going to be below the y-axis, and they might clump together in different ways, right? So this is not an alternating series. And just because it contains positive terms, contains negative terms, doesn't make it an alternating series. It really does have to fit the very specific mold that we talked about earlier. So that's why it's important really to make sure, first and foremost, that you're dealing with an alternating series. Because, right, like we just said, this one is not an alternating series. So if you go ahead and try to apply the alternating series test there and conclude anything from it, the premise is already flawed. It's not an alternating series. So whatever conclusions you get, you're not guaranteed that they're going to actually be true. In this case, though, we do see that this is an alternating series. And if you go back and you saw the table that I wrote out, you'll see that a sub n is n over 2 to the n minus 1. Right? Those are the non-negative. Those are all the like positive terms in the series that I wrote out. The denominator is always a power of 2, specifically to the n minus 1. So at this point then, what we're doing is we're going to run through the checks of the alternating series test. The first one being, is it true that the limits as n goes to infinity of n over 2 to the n minus 1 equals 0? That's again where I'll send you back to some of the work that we did for sequences where we talked about these different ways you can establish these limits. Take a look at video 5.2 for that. We did a very similar limit in that video actually. Actually, I believe for that one I was doing the limit comparison test, talking about the same types of strategies for evaluating these limits. And just like I mentioned there, right, this limit goes to this n goes to infinity. This n also goes to infinity, right? We're taking n to infinity. So it seems like this thing goes to infinity over infinity. Not quite sure what it is. You know, you might be, if you learned L'Hopital's rule, tempted to apply L'Hopital's rule, but you don't need that. All you need is some version of a growth argument, right? Do exponentials grow faster than linear functions? Yes, they do, much faster. Here's the exponential, here's the linear function, right? And then that difference is getting larger and larger and larger. So even though the numerator and denominator are going to infinity, the denominator is going to infinity much faster. So this does in fact give you 0 for the limits. So we will consider that verified. And then number 2 here is the last part, right? Which one of these 3 are we going to go with, right? Are we going to verify this version of the series' terms being non-increasing? Or are we going to go with this version, or are we going to go with this version? And as I said, depending on which problem you're doing, one might be easier or more straightforward than the other. So we saw here that in this first example, that this one down here was the more straightforward one. I'm going to actually write out that same one for this example. I think it's the more straightforward one. And then I'll show you at the end the other 2 and talk about, why they're a little less straightforward, in my opinion. So I'm going to try writing out an plus 1 minus an and verifying that it's less than or equal to 0. So let's start with an. So that's an. So that's an easy one. Okay. And then an plus 1, everywhere I see an n, I put in n plus 1. So the numerator becomes n plus 1. Oops, I should have put a minus 1 here for an. So back to an plus 1, the numerator becomes n plus 1. The denominator, I just add 1 to n. So n minus 1 becomes n. So that's 2 to the n. Okay, and I'm subtracting these. And I want to know if it's less than or equal to 0. So to figure that out, I could find a common denominator, right? To do that, I could multiply here by 2 over 2. And then that would give me, this part stays 2 to the n plus 1. That would give me in the denominator a 2 to the n. And then in the numerator, that would give me a 2 times n. So now I have a common denominator. And I have n plus 1 minus 2n. And therefore, I have n minus 2n. That's, let me keep the 1 first. And then n minus 2n is negative n divided by 2 to the n. And at this point, you can see that we're getting closer to what we want. We want this to be either 0 or negative or just less than or equal to 0. So what's happening here is that if n equals 1, right, this is 0 for n equals 1. That's the starting value of our series, right? N goes from 1 to infinity. If n is bigger than 1, if n is bigger than 1 here, then 1 minus n is going to be negative, right? If n is 2, 1 minus 2 is negative. If n is 3, 1 minus 3 is negative. So less than 0 for n bigger than 1. And this is exactly what we want to show, right? There may be some times when it's 0, there may be some times when it's negative, but in all cases, it is less than or equal to 0, right? That's what we wanted to show, so check. So we verified both of these conditions, so this is another convergent alternating series. All right, so I promised I would write out the last two variants of this just to show you what it looks like. So an plus 1 minus less than or equal to an, what does that look like? Well, so we wrote out our an plus 1 term here. So that is here. And then our an term is here. Okay. And you can see that this is a different way to deal with the inequalities, right? What you might want to do here is cross multiply and then get it to a point where there's a simple condition that then you can reason is true, and then the formal proof would start from that reasoning and go backward and establish that. But again, that seems to me a little less straightforward than what we did down here. And then so the next one is, what about the ratio of these, right? And you want to show that's less than or equal to 1. So we have n plus 1 over 2 to the n. Divided by a sub n, so that is like multiplying by the reciprocal, less than or equal to 1. This one is not too bad, right? So if you just multiply things into their respective places, this 2 to the n minus 1 divided by 2 to the n gives you a 1/2 in the denominator. So it's n plus 1 over 2n. You could, again, keep going here with some algebraic manipulations and later argue that this is less than 1. For the n bigger than or equal to 1 range that we have. But again, it's a little less straightforward than what we did over here, in my opinion. So all of this is to say, to zoom out here, again, when you are verifying this last condition of the alternating series test, realize that you have all these different options here. You have 3 ways to do it. And you might want to think down each one of these roads before you actually go off and pick one to see which one might be faster or you might be more comfortable doing. Thanks for watching.